So, I just started the streaming. Let us wait a few seconds to understand if everything is okay. Okay, seems so. So I can move on.
You could click so you're very wide the thing. You could click yourself a little bit on the left and on the right.
Like.
Or just like, let's do this way. Shift just the window on the right. You know.
Okay. And then.
Yeah. No. Yeah. This way.
That way, yes. And then I can move myself like here.
Because otherwise half of the title is.
Okay. No, it should be better. Is it really better? Yes. Okay. So, I guess we can start now with today's exercise. We will see another example of a registration problem. In particular, we will see projective ICP. So we will start talking about cameras and points on an image. Then you will go deeper in this in the next lesson, which is on essentials in computer vision. Anyway, during this lesson, we have two focuses. One focus is on the topic of projective ICP. So we want to understand how to use the camera model, how to represent a pinhole camera, and so on. But also, we will focus on how to develop a complete programming example in C++ to test an approach to a specific problem. So in this case, we will approach the problem of projective ICP using least squares. And what we want to do is we want to develop an application from scratch that allows us to test our approach, which in this case is least squares for projective ICP. So we will go very gradually through this and start with the simulation environment, with how to create the simulation environment, then talk about data association, camera model, then data association, and finally we will get to least squares. And we will validate each step soon after we've implemented it in C++. So the aim of this lesson is both to let you understand how to solve an ICP, a projective ICP problem, and how to develop an application in C++ to test your approach. So, if the introduction is more or less clear, then I can move on. We will be using C++, as I was mentioning, and I will try to explain as much as possible, or at least as much as so that when you go home, you can revise it by yourself and understand what's going on in the code. Okay, so let us introduce the problem of projective registration. We are given a set of 3D points in the word frame and a set of measurements. In this case, the measurements are 2D image projections of these points. And we want to find the relative pose of the observer minimizing the distance between the prediction of the measurement and the actual measurement. Meaning what? Meaning that in this case, in order to go from 3D points to points in the image, we need to take these points and project them to the image using the camera model. Now, we will go deeper into the camera model later, but what you should know right from here is that assuming that the camera model is known, so that assuming that you know how to project points in the camera frame onto the image, then the objective of the projective registration problem is to find the transformation from the camera frame from the word frame to the camera frame that allows you to minimize the distance between the prediction of the points on the image and the measurements that are points in the image plane. Okay, so the point is that assuming that you know the camera model, that is like assuming that you know how to project a point in the camera frame onto the image, then the problem of projective registration is the problem of determining the transformation from the word frame to the camera frame, which allows you to minimize the distance between the predicted measurement, which in this case is a point in the image, and the actual measurement. Now you can see the link with ICP of the previous lesson, because in ICP we were saying we want to find the relative pose of the word in the robot frame so as to minimize the distance between measurement in the robot frame and points in the word frame. In this case, we will be finding the transformation from the word frame to the camera frame so that points in the word frame transformed into the camera frame and then projected in the image using the camera model are as close as possible to the measurements, which are points in the image plane. Of course, when you will see the actual camera model and then the prediction function, this will be even clearer. But up to now, what is important is that you have this idea that points in the word frame should be expressed in the camera frame and then projected in the image. And what we want to find is the transformation from the word frame to the camera frame that minimizes the distance between the prediction of the points on the image plane and the measurements which are on the image plane. Okay, if you are, if you feel familiar with this idea, then I can go on. It is not important that everything is super clear, because at this point, you do not know what is the camera model, so it is quite normal that it is not, super clear, but at least the idea should be familiar, Okay, do you want to ask any questions so far? No. Okay. Then I will go on with the presentation. Okay, this is an assumption. In this case, we consider that the data association is unknown. So we will be performing data association as well. And we will see how. Now let's go through the outline finally. We will go, as I was saying, we will walk through a complete programming example. So we will start from scratch, build our measurements, so we will build our data set, and then once we have our data set, we will implement and check the data association, that the data association is working, And only after we have our data set, our camera model working, and our data association working, only when all these steps will be implemented and validated, then we will go through least squares on manifold, which is, say, the most important part from a theoretical point of view. But as in this particular exercise, we are also trying to let you learn how to develop a complete programming validation of an approach, then we will go through all these steps with the same importance. So again, we will start from the Pinhole camera model. I will first explain you the Pinhole camera model from a theoretical point of view, and then let you see the implementation of the camera model. Then I will go through data association. I can say that we will be using the distance map, but I will go into much details later. And then finally, we will be implementing least squares on manifold for this particular instance of a registration problem, which is the projective ICP. All of this will be in C++. Okay, so let us proceed very gradually. As I was mentioning, we will follow this step. We will start from simulation environment. Of course, as we are starting from scratch, then we need to implement also methods that build our world, say. So we will construct our own simulation environment. And we will be doing this, taking particular focus on the fact that we want to visualize as much as possible. Okay, I will go deeper into this later. Then after our simulation environment is built, we will move to the synthesis of the sensor model, which in this case is a Pinhole camera. Then, once we have checked that the sensor model is working by testing it on our simulation environment, we will move to the data association. After having validated the data association, we will finally go through least squares and then integrate all the parts. As I was mentioning, when you implement something from scratch, it is very important that you do a validation after each of the steps. Otherwise, problems increase, and you do not know where to look at. Okay, so let us move to the sensor model. If you have any questions, just raise your hands at any time. So, the simulation environment. In principle, our world could be composed of randomly drawn 3D points. But this won't help us to visualize our results. In robotics, we have the opportunity to visualize almost everything. And the idea is that when you implement something, then you should visualize as much as possible, ideally everything. So if you choose to use random 3D points, then checking that the camera model, that the sensor model is correct is more difficult than if you choose points arranged in specific patterns. Meaning that if you choose segments, for example, as your simulation environments, then you know what you should expect from your camera. Of course, lines remain lines. So the idea is that a very simple, say, debug method would be to check that lines remain lines. So, to give you an idea, the idea is that we should choose our simulation environment. As we are creating our simulation environments by ourselves, because we're doing everything from scratch, then it is very convenient to choose points in the word that are arranged in specific patterns, in patterns that you can easily visualize and easily debug by visualization. Say visualization should be your first, your immediate, your very first debug method. Okay. To summarize, our simulation environment will be composed of segments, of lines, so that it will be very simple to check that everything is working. Now we can have a quick look at the file points.utils.h and .cpp to see how the word, how our word is generated. And you will see functions that use the Opencv library. Now, Opencv is a computer vision library for C++ language, which is very efficient and does many things. We will use it only. We will use only its basic functionalities, meaning that we will use Opencv only for drawing circles in our image. Again, in the slides, you see that we design, you should design your program to be debugged, first of all, through visualization. And in this case, debugged through visualization is immediate if you use lines or segments. Okay, so I was saying that we will see, first of all, points.utils. Okay, so points.utils is a file that you find in your folder 24 Projective ICP. And here we have a collection of functions in a namespace which is called PR. Now, let us go through some of these functions, not all of them. So as you see, we have the put points on a segment, which is a function that takes the start of a segment, the end of a segment, the density of the points in our word, in our simulation environments, and gives you a set of points along the segment going from the start point to the end point. Then we have the function makeWord, which takes the lower left bottom and the upper left bottom of our word, that are because you have to choose points that are in the field of view. And then you say how many segments you want in your word, what is the density of the points in the word, and this gives you the set of points. And then you have other functions. The last three are for visualization. We will only see draw points. You can then have a look at draw distance map at home. And then you have put point indices, which is an auxiliary function to go from float to integers. Because, of course, on the image we will use int to access the image. Okay, so let us have a look, for example, of at makeWord. Okay, so in the makeWord function, as you can see, we use a lot this namespace eigen, and in particular this is because we use eigen in this C++ program. Eigen is a library for for linear algebra, a C++ library for linear algebra. As OpenCV, it is very powerful. You can do many things with it. In this exercise, you will see eigen, and it will be used only for defining data structures, such as vectors or matrices. Again, as an introduction to this code, go to the file defs.h to find all the definitions that we are using in this exercise. So, as an example, while a vector 3f, which is a vector of 3 elements which are float, is already given as a definition by eigen, other types, such as a vector of dimension 6, is defined through this type def. Okay, now let us go back to the exercise. So in order to build your word, what you do is you take the number of segments that you want in the word, and you do a loop over the number of segments, and for each of these you take a starting point, an end point, and then you call the function putPointsOnSegments 3D to obtain the set of points, a set of points according to a specific density lying on the segment from P0 to P1. Now, the only function that you need to know in this make word is the drandom48 function, which is a C function giving you a random, pseudo-random number from 0 to 1. So in this way, you are extracting randomly a starting point and an end point from the set of points which happen to be in the field of view of the camera. Okay, I wanted to show you very briefly this file, but of course this is not the real focus on the lesson. We will go much deeper into, for example, the camera class or into the least squares machinery. It's just for saying again that our choice in this case is to have a simulation environment which is composed by segments, and that in your points utils you find all the functions in order to produce this particular data set. Okay. If there are no questions on this, I can, okay, I want to ask you if you want me to comment also this function here, which should produce a set of points in the segment from start to end, from the start point to the end point with a specific density, or not. And then if you have any other kind of question. So do you want me to go through this, or you feel that you want to do this by yourself? Okay. So could you repeat louder a little? Okay, okay. So I can go on. Okay, let us talk about our sensor model, about the pinhole camera. So assume you have a point, PW, and first of all, X, C, Y, C, Z, C in this image is the camera frame. Then we have F, which is the focal length, and we have U0, V0, which is the principal point. The principal point is the point of intersection between the z-axis of the camera and the image plane, while the focal length is the distance between the origin of the camera frame and the principal point. having given these definitions, we can simply obtain a point, the coordinates of a point in the image plane, starting from a point in the camera frame. How do we do this? We do this by considering the similar triangles here. The first one is this one, and the other one is this one. If you consider these triangles, which are similar, then you should see that u over u0, u minus u0, which is this segment here, over the focal length, should be equal to x w, the x of this point here, over the z of this point. So if you go and see this equation here, this equation is precisely what I just said. So u minus u0 over f is equal to x over z. And at the same time, if you consider these other two triangles, this triangle here and this other bigger triangle here, then you can notice that they are similar, so that again you can write that v minus v0 over the focal length should be equal to y over the z of the point. So that in this way you can easily check that given a point x, y, z in the camera frame, then you can obtain the point in the image by applying this transformation here. Now, this transformation can be compactly rewritten if you isolate the camera matrix, which has this shape here, f and f in the first block, and then u0, v0 in the third column. And you apply an homogeneous division, a projection operator. So if you go and see the product of the camera matrix times PW, you will see that x camera is equal to fxw plus u0zw, while y camera is fyw plus v0zw, so that indeed x camera and y camera is precisely equal to this expression multiplied by zw, which is equal to z camera though. So that if you take a point obtained by the product of the camera matrix times the point Pw, and then do an homogeneous division, which means divide both the x and the y coordinate by the z, then you obtain precisely the point in the image. Okay, now we will rewind for a second. So, are you okay with the explanation of the similar triangles? So, does this formula here, is it correct according to your understanding of the topic? This formula here. Because here, okay, say UF and VF, in this case is centered in the principal point, so that in this particular example, it would be a 0.
Where the pixels start. The pixels start in the top right corner.
Yeah.
The principal point projects into the middle of the image.
Okay.
So you indicate
Yeah.
the translation. That moves the origin of the camera in the top right corner. Or moves the principal point.
Okay, so thank you for the question. The question is, why do we have this translation here, U0, V0? And the point is that usually you do not use this coordinate system here. You use a coordinate system which is centered in the upper left corner of the image, so that the principal point has non-zero coordinates. But your colleague was right in saying that according to this picture, I would expect the principal point to be in 0, 0, so that here I want to expect this translation. The explanation is that there is a translation here because the reference frame of the image is here in the upper left corner, so that the principal point has non-zero coordinates, u0, v0. And this is how we can explain this. Okay. So, now, if you are convinced of this formula here, then we can again rapidly go through this and move on, unless anybody has another question. Okay. So, very rapidly, this projection of KPW is in the end just a compact way to write this expression here. Because if you do the product K times PW, then you obtain something which is this expression times ZW, so that when you go and do the homogeneous division, then you have exactly the point in the image. Okay. So, can I move on? Yes. Okay. So, now, this is interesting. Okay, okay. So, in general, the camera frame does not coincide with the word frame. So that, in general, we should first compute the point in the camera frame and then apply the operations that we have seen in the previous slide. So, given a point in the word frame, we should first of all bring it to the camera frame, then multiply it by the camera matrix, and finally do the projection. This happens to be the whole transformation that allows you to get a point on the image given a point PW in the word frame. So you go, you take it, bring it to the camera frame through this transformation, then multiply it by the camera matrix, and finally do the projection, and now you have a point on the image. Now, I believe that it is convenient to reformulate the projection, the ICP projective ICP problem, because now it should be very clear. So the projective ICP problem is the problem of finding the transformation X from the word frame to the camera frame, which minimizes the difference between the predicted point and the actual point on the image, and the actual measurements, between the predicted measurements and the actual measurements. Okay. Now also the problem should be very clear, super clear, which probably was not before. So, are you all right with this? Can I move to the CPP? Okay. Seems so. So, and now, talking about the implementation of the sensor model. We will implement a class. Now, as you might know, CPP is an object-oriented language. So classes are very important in C++ language, and you should use them as much as possible. In this case, a class is a very suitable struct for representing our sensor model, because a class has some members and some methods that allow you to operate, do operations on these members. Intuitively, we can understand, and then we will see the code, that the members of the camera should be the pose of the word with respect to the camera and the camera matrix, because in the end, these two elements, the camera matrix and the pose of the word with respect to the camera, represent all we need to know about a specific camera, at least in the case of a pinhole camera. And then we should have a set of methods, functionalities, which allow us to operate on points and obtain their projections onto the image. And then we will test our sensor model and see that everything works. But first of all, let us move to the camera.h file. So the camera.h file is in the same namespace as the point utils. It's called the PR, and it's the class of a pinhole camera model. Now, as I was mentioning, we have both members, which might be public, private, or protected, and methods that are functions to operate on them, and eventually on specific inputs to these functions. There are some peculiar functions, methods, such as the initializer, which is the function called on creation of the object. In this case, the initializer takes a number of rows of the image, the number of columns, the camera matrix, and the word to camera pose, and uses these inputs to give a value to the members, which in this case are protected, which have the very same names of these inputs. So we have that a camera, again, is characterized by its camera matrix, by the word to camera pose, by the dimension of the image, which is given by the number of rows and the number of columns. And on creation of the camera, we specify what's the value of these members, of these objects. Again, you can see that we are using eigen, and we are using matrices and isometries. Isometry is the class we use for transformations, because it has a rotation part and a translation part. Okay, having said this, we can go to the most important function of the camera model, which is the project point. The project point method takes as input a point in the word and gives you a point on the image by applying the function that we have seen in the slides. I want you to notice that, for example, the point in the word has this attribute, is a reference to a vector 3f. It is important in CPP that you can use references, past references to functions instead of copying the objects. But I won't go deeper into this. It's just for mentioning this ampersand means reference, and anyway you need this in your life, then go and check to start, say, understanding how CPP works. And the other important thing is that here we are passing the word point as a const, because we do not want this method to change the word point. Okay, I promise from now on I will only talk about theory, no more C++. Okay. So, how does the project point works? We first of all obtain the transformation, the point in the camera frame. How do we do this? We take the transformation from word to camera and apply it to the word point. Then we check that this point is in front of the camera, because if it is not in front of the camera, then we cannot see it. So this function should return a false Boolean value. Then we can apply the camera matrix and do the homogeneous projection. And after having done this, we will check whether the point is in the image or not by checking whether its x and y coordinates are in the image which has dimension given by the rows and the columns of the camera. Okay. Maybe the only thing we should go a little bit deeper into is this homogeneous division. How do we do the homogeneous division? We take the first two elements of the projected points. This head function of eigen means taking the first and then you specify how many. So we're taking the first two elements of the projected point and then divide these coordinates by the z coordinate of the projected point. The vector 3f, eigenvector 3f, can be accessed using this, has these methods, x, z, and y, which allow you to take the corresponding coordinate. Okay, so here you're saying I take the first two and divide by the z. Okay. Is it clear? Okay. I just mentioned this. You can have a look at this at home. Project point equals project point on all the points. Okay, so now here we are in the folder 22 Projective ICP. Then I show you how you can make and run the tests here. So here what we do is we make a directory which is called build. Then you move to build. Then you do cmake dot and then you can do the make. And now the make is going on, and then we will have our executables in the folder executable. Okay. Now what we want to see now is the test of this camera model, which means that we take a set of points in the word frame, project them through this project point, which is a method of the camera, and we will see that lines become lines and so on. And we will have the opportunity to zoom in, zoom out, move left or move right by using the keys WASD on your keyboard. Okay. So just a few seconds to compile. Okay, then you do cd executables, and then you go with camera test. Okay, and now I can move left and right and then forward and backward. And as you see, it seems that okay, it's realistic that these lines were generated by lines in the word. By using the keys W, A, S, and D. Okay. This is D, now D, A, D, sorry, S, and W. Okay. I would say we're done with this. If there are any questions.
I'd like to say something to the folks. I mean, so folks, one thing fundamental when you are
sort of things is that you need to construct a simulator first. So once you have a problem, like I'm talking when you do it for real, not when you do the exam or the stuff. When you're assigned a problem like, shall it be a filtering or a system or whatever, the very first thing that you need to do is to validate that the theory, that the model that you have in mind corresponds to the reality. And to this extent, you build a simulator. If you consider what Barbara has done in these slides, it's basically saying, okay, I think I know how the camera works. Now let me put a bunch of points in the world and let's move a camera to figure out if what I sense, what I measure is responding my intuition. Okay? And this is fundamental because we have done two things in once. First, we have constructed a simulated environment where we have complete control of the data, and so we know what is the truth. We know what would be the position of the camera once we will impose it because we are the one that are issuing it. And the second thing that we have is that we will be able to, how to say, have the measurement model already, right? Because you need the measurement model in order to predict the observations, which is what you have. Is that clear?
Yes.
And so, like, this is a fundamental step. And also, don't rely on the numbers on the screen, because believe me, the numbers of the screen, like you spend twice the time in interpreting the number of the screen on the screen rather than having a proper visualization. Just like don't be lazy at the beginning, because you will pay your laziness at the beginning later on over multiple days. That's my suggestion. It's like of a veteran.
I just want to say that for these kind of standard things, when we want to implement them ourselves, it's best to have an oracle, right? An oracle, right? Like
an oracle, yes. You start exactly. Your colleague says it's better to have an oracle. Yes, you start with an oracle, right? Because at least you know what you should measure. If I swing the camera on the work, and then I start processing the data from the camera, right? Then I'm putting too much stuff together, because if I would really use a real camera, then I would have the issues that I have with the feature extractor, the issues that I have with the feature detection. We will see it tomorrow, but a lot of issues I will encounter, and then I will think instead of focusing the sickness, focusing the bug in where it is, because that's the only thing that is there. You would just like have a much larger system. Now, like not in Italy, but in a normal country, the doctors, if they would have to, could heal you, or like the mechanic. When he wants to really fix something, he takes the part, puts it on the desk, does his own things, and then he puts it back. Right? This is how you debug things, divide and conquer. Right? And the same doctors would like to do if they could.
What I mean is that some famous libraries implement. What I mean is that famous library we implement the same thing. So
yes.
when we want to implement them ourselves to training, we're gonna have one input and then give it both to the famous library and to our code and see that we have the same output. So that a way to test.
You're saying I would like to have so like instead of doing this implementation myself, I could just like use.
No, I do it myself and to check that it is correct.
You mean you want to build a simulator yourself and then check it against an external library, an external system. Yes, of course. I mean that's what you can do. But once you have your eyes in front of the problem, your colleague says, okay. But in order to even further validate this step, I could use some external simulator and then check that the results of the external simulator and of my simulator are consistent. Yes, this is true, but this is true. Often, once you are engineers with stars, it's called to solve such a problem. They don't have a simulator, so they have to build it themselves. But you could do that. The thing is that, and this is also beneficial, because what you might have is that sometimes the fancy simulator returns you the data in a format that you don't realize. Like for instance, to my colleagues, like Luca and so on, they were like using an external software for doing some reconstruction, 3D reconstruction thing. Then it turns out that this item was producing the inverse rotation instead of the rotation, right? That you might expect. But the direct translation. So the translation as of the camera in the word frame, but the rotation of the word frame with respect to the camera. sometimes when you use external things, you really need to know well, to read well the documentation of what is what. All right? So now I go back to my scrum.
Okay. So.
Sorry about that.
Okay. Want to be a little bit smaller. Okay. And yes. If you go to camera test, you can see that each key is associated to a specific motion. And then what you do is you apply this motion to the camera so that indeed pressing a key corresponds to doing a motion on the camera. Okay, I just wanted to notice this. Then let's move on with the presentation and talk about data association. Assuming that we have a reasonable guess of the camera and that the points are sparse enough, we could think of a nearest neighbor strategy. We know that there are some heuristics in order to make the nearest neighbor strategy more robust. But anyway, the idea is that we project a point onto the image and then assign these points to the closest measured point onto the image. However, if we do a naive implementation of this closest neighbor approach, nearest neighbor approach, then we will take O and 2 operations for each least squares iteration. Why? Because for each least squares iteration, we have a different estimate of the word-to-camera transformation, so that we have a different estimate projection of the word points onto the image, so that for each least squares iteration, we should project the point onto the image, and then for each point, which is ON, for each point we should find the nearest neighbor, and then it's n checks for each of the points, so that in the end we have ON times n square operations. But we can do better than the naive implementation because we can use the distance map. And this is because image points lie on a plane. And the measurements on the image do not change during one alignment, so that we can build the distance map once for all and then use the same distance map on the measurements for all the iterations of least squares. But once you have a distance map to query, then the complexity to obtain the nearest neighbor for a given point on the word frame projected onto the image plane is constant, is O1, because you only need to access the matrix, say, together with the distance map, you have the information of what is the nearest neighbor for each point in time O1. So that the complexity of doing data association using the distance map is ON for each least squares iteration, because you have n points and each of them costs O1. So it's ON. Okay, and this is for saying that the reasonable thing, the convenient thing to do is you build your distance map on the measurements, and then you query your distance map on the points at each least squares iteration, on the projection of the points in the word frame at each least squares iteration. Okay, does it seem, do you feel comfortable with this? Now, of course, using the distance map means using a nearest neighbor strategy with gating, because you decide the maximum expansion of the distance map, but you do not have lonely best friends and lonely best friends. Anyway. Okay. Are you okay with this? Yes. Okay. Then let us move to the C++ implementation. So, as I already mentioned, we expect to compute a distance map on the image based on the measure points just once for each alignment. And then at each iteration, we just query the distance map to find the measured point, which is the closest one to the projection of the word point that we are considering. Okay, so in the C++ implementation, which we will see now, we have a class, again, the distance map correspondence finder, that has some attributes, but these are, say, members, the image size, the points on the image. Now, the points on the image are more like inputs of the distance map correspondence finder, because you ask what are the correct correspondences for a specific set of points, but we are putting them in the attributes because in the C++ implementation they will be members of this class. And then we have the maximum distance of the expansion of the distance map, which is a proper parameter of the algorithm. And then what we expect the distance map correspondence finder to do is to initialize the distance map, so to compute the distance map or call the computation of the distance, and then to query for correspondences. We expect that we can give a set of points and retrieve the set of correspondences with the measured points. So, we will be talking about how to test this later, but now let me show you the distance map correspondence finder in the code. First of all, let us give a very brief view at distancemap.h and distancemap.cpp. The distance map correspondence finder class, which was mentioned in the slide, relies on the distance map, of course. And the distance map is itself a class which is derived by the matrix, a matrix with a specific type of entries, with a particular type of entries. The entries of the distance map are cells called distance map cell, which are user-defined, and indeed at the top of this distance map.h file you have the struct distance map cell, which has these members and the constructor. Now, the distance map cell, of course, is a specific type of entry, is that type of entry that we use for the distance map, because it has to collect all the information that we need in order to compute the distance map. Now, the information that we need in order to compute the distance map given a set of points is we need to know which is the parent of our cell, that is the closest occupied cell, and we need to know the distance from the closest cell. To make the access easier, then we also have the row and column indexes. But the important thing is that you need the pointer to the closest cell and the distance to the closest cell. Okay, then you have a constructor which allows you to initialize all these fields. The parent with a null pointer, the distance with a maximum value of the int maximum, the rows and the columns. Okay, having said so, I was mentioning that the distance map is a matrix whose elements are distance map cells. We have some methods. Some of them are auxiliary methods, such as find the neighbors and the toImage methods, which you use for visualizing and then for finding the neighbors to a specific cell. And then we have a compute function, which is endowed with the computation of the distance map. Other auxiliary structures are the distance map cell Q, which, as you imagine from the lesson over the distance map, is a priority queue on specific type of entries, once again, which you use in order to access the cells while computing the distance map in the algorithm compute. Now, you are supposed to already know how the distance map works, so I will only go very quick through some lines of the compute so that I can go through the distance map correspondence finder, which is the most important class for us. So, in the compute, we take as input, which has this const definition. We take an image of ints, and now the idea is that in this index image we should have a value which is valid. We should have a valid value only in those points from which the distance map expansion starts. That is, only in the occupied cells, only in the measurements. This index image has valid values, that is non-1, only in those points that we want, from which we want the expansion to start, from the measured points. And then what we do with the compute? Yes?
This is my fault, because that's my fault, my mistake of the design. So, I mean, the idea is that I'd like to have a function that produces a distance map, right? That's it. In order to produce the distance map, what is the input? The input is a set of points, right? I could have a set of points in the book, or on the image plane, right? Once I have a set of points, I could start expanding around this set of points, and I could be happy with that. Do you agree, folks? All right. Now the question is like, if I would do so and I would have anonymous points, then I would lose the possibility of figuring out which point is which. Because the distance map just tells me the distance to the closest point, but it doesn't tell me which one of the closest points. Okay? So I need to pass to this the identity. Now, considering that this program here works on a discretized fashion, my problem was, how do I feed to this system a matrix, something, a data structure, that preserves the identity of the points that I put in. So I want to know which one is the first, which one is the second, which one is the third. Okay, guys? You follow me? All right. So now, like what did I do is like to say, okay, you know what? I have my input will be a grid, which is populated with -1. -1 means that there is no point there, right? Now, let's assume that this one here is the first valid point. So that now in this cell I will write a 0. Okay? Then -1. Then I have a second valid point. And then in this cell here, I will write a 1. The third point will have a 2, 3, 4, 5, 6. So basically in the cell ij of the distance map, I put a unique value, a unique positive value, that denotes that it's unique in the entire map. Do you agree? Do you understand? I have my points, the first, the second, the third, the fourth. So in this grid, I just like put a positive value in correspondence of the cell which is occupied by that point. Okay? Now, by doing this and putting a positive unique value, I'm automatically putting inside the distance map, inside this int map there, int matrix, int image, I'm automatically putting the potential indices of a vector that contains the points. So if I have a vector that contains, for instance, the point 1, 1, and then the point 3, 7, and then the point 4, 8, and so on, this will be the cell number 0 for cell number 1, so 3, and so on, right? Now, what will happen here is that in the distal matrix, which is initially in the int map, which is initially, do they see?
Yes.
Maybe I can do this. Right. In the distance map that is initially initialized with all -1, in position 1, 1, which will be this, I'll put a 0. Right? This is the position 1, 1. In position 3, 7, so 0, 1, 2, 3. 3, 7, well, it's far below, but it says way that this is position 7. So in this location over here, I would put what? I would put the number 1. Okay, guys? Is that clear? So this is a way that I can pass a data structure to the system, which is already populated with the image variable. Okay? Clear? That's it. And so this is the meaning of this int image. Once I will have the distance map that will be computed aside, remember that in the distance map cell, I automatically have the index of the parent. Okay? So I have the pointer to the parent. So for me, it would be sufficient either to go to the parent through the pointer to the parent, so which is the closed cell, and then to extract the row and column and look up the index, or I could straightforwardly put there the index there. And so automatically I would relate it to the pointer in my array. Is that clear? Just a mechanism of bookkeeping. Yes? No? Yes, that's it. Correct. Thank you, sorry.
Okay.
It was my fault, and so, yeah.
Yeah.
Maybe you have to minimize yourself.
Yes. I'm very, very big now. Okay. Here. Okay. So having said so, you can easily read this distance map compute and in particular go through this loop where we look at all the neighbors of a specific point. And if we find that the distance from the current parent is less than the value of the distance already written for that specific point, and that this distance is less than the maximum distance, then we update the parent of the point that we are considering, and we update its distance, and we write in this int image IMAP the value of the parent index, so that as the professor was telling you at the blackboard, we will have that by accessing this int image at R and C rows and columns corresponding to the specific point, we get the index of the parent. Okay, and I was very, very quick on this, but I guess you have already seen an implementation of the distance map, so the only thing that might be different from that one is this use of int image as a bookkeeping structure. Okay, the rest should be quite familiar. But if you have any questions or want me to go deeper into this before moving to the distance map, correspondence finder, just tell me. Okay, I will let you a few seconds to digest. Okay, seems okay. So now let us move to the, having briefly talked about the distance map, to the distance map correspondence finder. Now, in the test file, and you won't have to deal with the distance map directly. What you will be dealing with at high level is the distance map correspondence finder, which is the class responsible for initializing the distance map and then computing the correspondences between points in the word frame and points on the image. Now, the correspondence finder has a set of private protected members as usual. Some of them are proper parameters, such as the maximum distance expansion, the number of rows and the number of columns of the image. Some others are members which we use for computing stuff, such as the distance map. The float image, distance image, is just for plotting the distance map, and it's an image of float which contains the distance value for each cell, for each point in the matrix. Then we have indices image. This indices image will be our bookkeeping structure, because in this bookkeeping, in this indices image, we are going to write the index of the nearest neighbor when calling the compute of the distance map. So this indices image is our bookkeeping structure. And then we have our correspondences vector and our reference points. If you have a look at the depths, then int pair vector should be a vector of pairs of images. Okay, yes. Int pair vector is a vector of pairs of ints. Okay, probably I said images, I wanted to say ints. Okay. So, in the end, this distance map correspondence finder, as the name suggests, should take reference points, it should take the current points and compute this vector of pairs of ints, which is the vector of correspondences between the points in the word frame and the points and the measurements on the image, which in this class we call reference points. So if you go and see, apart from the init and compute function, which we will go a little bit deeper into details, the other methods of this class are the getter of the correspondences, the getter of the distance image, and the getter of the max distance. Now, the distance map correspondence finder is constructed through this distance map correspondence finder, which has no arguments, and it is initialized through this init method. Now, this init method, if you see, takes as inputs all those data or parameters which are needed for the distance map to compute, because it takes the maximum expansion of the distance map and the reference points, which in the end are the measured points in the image. It also takes the rows and the columns of the distance map. So if we go to the init function, then you can see that what we do in the init function is we set the maximum distance value, we set the reference points, the measurements, we set the rows and the columns, and then we compute the distance map according to the current, say passing it the maximum distance, the bookkeeping structure which tells the distance map the points from which to expand. So there are some details which I do not have time to fully develop here, but the important thing is that the first argument of the distance map is a reference to the bookkeeping structure, where we will be able to find the closest, the nearest neighbor by simply accessing a point through its row and column indices. Okay? So, unless you have a specific, unless you want me to go deeper in details in this, otherwise I will just go.
You can give them an idea of what the indices image will be.
Okay.
Maybe, let's imagine that this is my structure. Okay. That I have a point which is named 1 here, and a point which is named 3 here, right? Let's imagine that. Then I proceed with the expansion of the distance map, and what I expect is that there will be a line, no, orthogonal to this point, where from this side of the line, all the points will be closer to 1, and from this side of the line, all the points will be closer to 3. Do you agree with me? Okay, the indices image, or the indices, whatever I want to call it, yes, will be something like that. We'll have, in all this area over here, a lot of 1s. Okay? And in all this area here, we'll have a lot of 3s. In this way, if I do a lookup at a certain point, I immediately have the index of the point in the vector that is closer to that side. Clear?
Okay. Okay, now it should be very clear. Hope so.
Let's see if I manage.
Okay, so the init function of the correspondence finder takes all that you need in order to compute the distance map, and remember that the important thing is that the first argument of the function compute is going to be written with the bookkeeping structure that you see on the blackboard. And that you can use this indices image in your compute function of the distance map correspondence finder. As I was mentioning, the distance map correspondence finder has two methods, the init method and the compute method. The compute of the distance map correspondence finder takes the current points in the word as input, then the current points as input, their projections on the image already. Then it goes and accesses the bookkeeping structure in order to retrieve the index of the nearest neighbor, and then writes this reference index and current index onto the correspondence structure, which is a pair of int. And then finally it goes to write this down in the correspondences. Okay. Indeed, to be more specific, you take a reference to the num correspondences element of the vector correspondences and write it with the reference index and the current index. Okay, so summarizing the correspondence finder class is that class which is initialized, which has an init function that calls the compute of the distance map, and then uses the result of this call to the compute of the distance map to write down the correspondences given a set of points. Okay, so now I will show you the test of the correspondence finder so that we can move to the list squares. So, correspondence finder text. Now here what you can do is you can again move right, left, forward and backward. Now I'm pressing A. And unless I go outside, then the association works. unless I go further than the expansion of the map. You can change the value of the maximum expansion of the distance map by pressing minus, and then the maximum expansion reduces, or by pressing plus on the keyboard. Okay.
I mean, how was this test constructed?
This test is here in executables correspondence finder. Okay. Then you go and create your word, generate your word, and then you create an object of type correspondence finder. You create your camera, and then what you do is you wait through a while.
Well, in the initial correspondence finder, how is it initialized? Like which set of points?
It's a set, at the beginning the correspondence is perfectly correct, and then what you do is you
do a first projection, right?
you do a first projection, yes. You do a first projection of the points, and then each time you press a key on your keyboard, then the camera is moved, and then you need to recompute the correspondences.
Like you take an initial picture of the scene, you load the correspondence finder once, and then later on you just move the you re-render and you calculate the association.
Yes. And you have the, as you see, in this switch case, depending on the key that you pressed, you have a different motion for the camera. Then you update the position of the camera, and in case you pressed either plus or minus, the init function of the correspondence finder is run with a different value of the max distance. Okay, this was what I shown you before. The initialization of the correspondence finder is run again, but with a different value of the maximum distance of expansion. Okay, perfect. So in this way, we have also seen these two cases in the switch case, and. Okay, you can have a look by yourself at functions like draw correspondences, for example, and also draw distance map, but it's not so important, say. Okay, now, of course, here you can recognize that you are drawing your points. CV scalar is a way to encode the colors in using the Opencv library, and then you see that all points in the word are projected using the current estimate of the camera and then redrawn on your image. And then finally you compute the correspondences, and indeed here you're calling the compute of the correspondence finder over the current image points. Okay, do you feel comfortable with this? Now the good news is that from now on you are probably more familiar with, because it's all about least squares. Okay, so we will follow the usual methodology. So we'll start with the state and say that the state is again a transformation from the word frame to the camera frame. So it's the pose of the word with respect to the camera. It's an SC3 element. And SC3 is the group of homogeneous transformation matrices which are constituted by a rotation matrix and a translation vector. The state has an increment which we parameterize as an element of R6. And we have in particular a translation component of the increment and an angular component. Then we have the box plus operator, which is the usual vector to transform. once more, the vector to transform function is such that when the delta x is equal to 0, then the vector to transform of delta x is the identity. Indeed, the box plus operator should allow us to compute the chart around x, move by delta x, and then go back to the chart. Measurements. Measurements are Euclidean because measurements are points on the image, which means they are vectors of R2. Okay. I guess I can move to the prediction function. Actually, you have already seen it. We have seen it a few slides ago when talking about the camera model, and we have said that our prediction function is the concatenation of the projection operator to the linear transformation of xp through the camera matrix K. It's the last time I say this, but we take the point in the world frame, we compute its coordinates in the camera frame, then transform it through the camera matrix, and finally do the homogeneous division. You should recognize the prediction function of the ICP, which is precisely x times p. This will help us in the computation of the Jacobian. Okay, in the last two rows of these slides, you see these intermediate passages because again, we will use the chain rule in computing the Jacobian, so it is important that you have that you are able to look at this function as the concatenation of three operators. The first one is a transformation through x, then you have a linear transformation through k, and finally you have the projection. Okay. Now the error. The error, as usual, is given by the minus. It's a minus, and it's not a box minus because the measurements belong to R2. It's a Euclidean space. The error is given by the difference between the prediction of the point on the image and the measurement, which is a point on the image. And again, the prediction is the value that you obtain given the current estimate of the state. By expanding h of x, we have this expression where you can recognize the prediction function of the ICP. You can rewrite this error function in the argument x box plus delta x. Nothing special. You only have to substitute x with x box plus delta x. We do this because the Jacobian will be computed as the derivative of the error in x box plus delta x over delta x, as you might remember. Okay. So, are there any questions so far? It should be quite straightforward. It's similar to the ICP. Okay, so let us see how we compute the Jacobian. Again, the Jacobian, as we have seen also in the last exercise, is computed by taking advantage of the chain rule. So what we do is we consider that the Jacobian is equal to the concatenation, the product of the Jacobian of the outer function, which is the projection operator, with respect to its argument, computed in its argument, which is in the current estimate of the argument, which is p hat cum according to the previous slide. Here it is. Then you have this times the Jacobian of the linear transformation Kp, which is K, because the Jacobian of a linear transformation with K, which is a constant matrix, is just a constant K. And then finally you have the Jacobian of the ICP with respect to delta x computed in its argument, which is p hat n, if you go a few slides before you see this. Now, it is very important that you do not make a confusion with the dimensions. The Jacobian is as high as the error and as large as the dimension of the perturbation of the state. Now, the error, the measurement, and thus the error is two-dimensional because it's a point on the image. So the Jacobian will be as high as 2 and as large as delta x. If we go and perform this analysis also on the other matrices, then we see that the Jacobian of the projection operator with respect to the point P is as high as the output of the projection operator, which is 2. Because the homogeneous division gives us a two-dimensional point out of a three-dimensional one. So the Jacobian of a projection operator is as high as 2 and as large as 3, because P is three-dimensional. K, as you might remember, is a 3 times 3 matrix. And finally, you have the Jacobian of the ICP, which is as high as the measurement of the ICP, which is 3, because in ICP, in traditional ICP, we have points in the word and points in the robot frame. So this JICP is as high as 3 and as large as 6, which is the dimension of delta x. So we have a 2 times 3, then a 3 times 3, then a 3 times 6, which altogether gives us a 2 times 6. Okay, now, you already know the Jacobian of the ICP. It's a two-block matrix. The first block is the identity, and the second one is minus the skew-symmetric matrix, or the skew-symmetric in minus the point. The point is the argument of HICP, which is the point in the camera frame. The point to which the point of the word Pn to which the transformation x has been applied here. Only the Jacobian of the projection operator is new to you, but it is very simple because the projection operator gives you x over z and y over z, so that when you do x over z derived with respect to x, it's 1 over z, with respect to y is 0, and x over z with respect to z is minus x over z squared. Okay, the derivation of least squares is completed, so we can devote this last 20 minutes to the C++ implementation and see the final test running.
By the way, after implementing the least squares, I'd like to try a test without that association.
It's done already. Okay. Okay, so. Oh, okay, okay.
No, yes, I had a bit forgot how it worked, the box plus, so I was asking him.
But you know now? Or not?
Yes, it's...
okay, basically you apply a perturbation, minimal perturbation to the current transformation matrix. To this extent, what you do is that you inflate the minimal perturbation to a transformation matrix, and then you multiply it to the time. It's the motion on the chart.
So it modifies, but in a more appropriate way
try to go like, you know, in compartments. So going in compartments means that now we have list squares ready, and once we have list squares ready, we would like to test only list squares without taking into account the data association, right? So we're going to give it perfect data association. So we are taking the points. We know when we transform a point which point is which. So we could treat the list square thing with the perfect associations, and we want to see it converted to 0. And then we have another block independent from the rest, which is function. And then at the very end, we would put everything together. Sorry.
Okay. Yes. We will get back to this after we see the list squares class. So in a minute. Let's hope it's in a minute. Okay. In C++, we will write, as usual, a class for implementing something. In this case, we have a class for implementing the list squares solver. This class will have as members the points in the word, the points in the images, so the measurements, and it will have the current estimate of the camera pose and the kernel threshold, which is a parameter we use for making our estimation process more robust. We have seen the kernel threshold also in the last exercise. The important thing, of course, we are all mentioning these word points, image points, camera pose, and kernel thresholds as attributes because they will all be members of our class, but they have different meanings. Of course, word points and image points, for example, are inputs to our algorithm. But in our implementation, it is convenient that they are members of our class. This class will have a function to build the HMB matrix and a function to perform one list squares iteration. In this exercise, we will explicitly call the iterations one by one, pressing a key on our keyboard. In particular, we will press the space, and pressing the space will coincide to one iteration. So our list squares class will be doing only one list squares iteration and will be called explicitly for repeating over and over the iterations. So let us move to the code. We close the correspondence finder and the camera and go to the solver. So here you have the PIC solver, it's called. It's a projective ICP solver. You have an initializer, an init function, which gives to the solver the camera, an object of camera, a reference to a camera object. It gives the word points and the image points. So as I was mentioning, word points and image points are private members, are protective members of our solver, but they are set as inputs actually. And then you have some utilities like the getters of the kernel threshold, of the camera, of the inliers, of the outliers and of the inliers, of the number of inliers. It is very common in C++ that you use protected and private members and then use functions to get them, which are called indeed getters. And then you have one public function, which is called one round, which will perform one round of ICP, taking as input the correspondences between measurements and points in the word frame. And then you have protected functions, which are not supposed to be called from outside of this class, that are the error and Jacobian function and the linearize function. Now, the linearized function will take the correspondences and will build the H and B matrix. The one-round function will use the H and B matrix to solve the linear system. And finally, the error and Jacobian function will do exactly what you imagine based on its name. So, let us see the PICPS solver constructor just sets the protected members to given values. Then we have the init function, which again is used for setting the set of points in the word and the set of measurements, which in this case are called reference image points. And then we have the core of our class, which are the error and Jacobian and the linearized, the error and Jacobian linearized and one round.
Basically one-to-one from Octave.
Yeah, it's one-to-one from Octave.
It's syntax adaptations, if you can figure it out.
It's a very Octave-like implementation to make the reading more comfortable. So, for example, you can recognize that the error and Jacobian takes as input a point in the word, which is a vector 3f, a reference image point, which is a measurement, so it's a vector 2f. We have the Jacobian, which, as I was mentioning, it's a 2×6 matrix. And then we have the error, which is a vector 2f. Error and Jacobian are written, so they are not signed as const, while word point and reference image point are const. Then what we do is we use the camera to project the point. Finally, you see how the project point of the camera is used. And then once you have the projected point, you can compute the error as the difference between the predicted image point and the measurement. If you can remember, the project point of the camera can return false in case the point is not in front of the camera or it is not in the field of view, so we check whether the point is good or not. Then you again use a method of the camera, which is the word to camera pose, to get this transformation, word to camera. And then this is done in order to obtain the point from the word frame to the camera frame, which you need to compute the Jacobian of the ICP function. Then you remember that the Jacobian of the ICP has two blocks, and we are writing each of them. Then in this part, we are writing the Jacobian of the projection operator, which is a 2×3 matrix. And then finally, you can write down the expression of the Jacobian, which is the concatenation of the Jacobian of the projection, the camera matrix, which is constant, and the Jacobian of the ICP function. Okay. I guess I can move to the linearized because it should be really easy to read. The linearized, again, it's very Octave-like, so we have that this function takes as input the correspondences and the Boolean value, which tells you whether you want to keep the outliers or not. And then it assembles the H and the B matrix. It first sets them to 0, and then for each of the pairs, it computes the error for each of the pairs in the correspondences vector, which means for each of the measurements, it computes the error and the Jacobian by calling the error and Jacobian function, which are respectively a vector 2f and a matrix 2×6. And then in case the result is valid, which means the point is inside the field of view, then we can compute the chi value and understand whether the point is in inlier or not, update the structures which keep memory of this, and then finally update in case we have an inlier or in case we want to keep the outliers, then we update the H and the B matrix according to the usual formulas. So J transpose J and J transpose E. Lambda is just a scaling factor which allows you to scale down the contribution of the outliers. Okay. Now, finally, we'll see the only method which is public, the only method of the solver which is public, that is the one-round method. This one-round method calls the linearized function, which is the one we have just seen, in order to obtain the H and the B matrix. And then once you have the H and the B matrix, you can compute the perturbation by calling a specific solver. In this case, we are using the LDLT, which is a specific Cholesky decomposition provided to you by the linear algebra library eigen. In the slides, you find the whole set, you find the link to the page in the eigen website where you have a bunch of solvers and of Cholesky decompositions which you might try out. Okay. Now we have the last slides almost finished. So as the professor was mentioning before, we need to test our least squares first of all with known data association. So we take a set of points, we project them. So we start from an ordered vector of points in the word frame and obtain an ordered vector of measurements in the image, and do least squares and verify that when data association is given, the result is correct. Then once you have tested this, then you can move to the case without data association. Okay. Just very last hints before I show you these simulations. So last hint, validate the error when you implement the least squares part. Make sure that the error that when the system is the optimum, the error is 0. So make sure that when your estimate of the camera with respect to the word transformation is the ground truth, then the error function should return 0. And then ensure that your Jacobians are correct. So you can first compute the numeric Jacobians and then pass to the analytic Jacobians. This is the link I was mentioning about eigen on linear algebra solvers. Okay. So, in conclusion, and then as the last thing, I will show you the whole, the complete test running. Remember to apply a divide and conquer approach to your implementations. So divide the problem in smaller tasks that you can solve easily and that you can test and validate. In this case, we had 3 steps. The camera model, the data association, and finally least squares. And remember to always visualize everything, which means build your own data set, your sandbox, in such a way that you are able to visualize the results and make sure that everything is working. In our case, we have chosen as a simulation environment a set of segments, which makes debugging by visualization really simple. Okay. Slides are over, so I close them and open the terminal to let you see the last 2 executables, which are picked solvers test, in which we assume that the correspondence is given. Pip solver.
No, PCP.
Ah, ICP, sì, ne faccio. Ah no, è giusto. Allora, pip, ok, solver test. Okay, now correspondences are given. Again, I can move around. Then, in order to perform one iteration of list of squares, you press the enter. Sorry, the space, not enter, the space bar. And so, as you see, this is one iteration, this is two, and it's almost there. On the other way, here, one iteration, this is two, and it's almost there. Okay, and then you have PIC complete test, which is the same, but data association is not given, so that you will see the distance map that we use in order to compute the data association. And indeed, here you can see the distance map, which is used for computing the data association. Now, data association is not perfect, but it's correct. So we can press space, and the algorithm converges. It's a little bit slower, but of course we do not have data association. So now data association is broken. It does not seem to, it's too close, too far, sorry. So it is not able in this case to converge because we have started from too far. So data association was not correct at the beginning, so we are not able to converge. Anyway, you can play around with it. Now, in order to be able to play around with it, you only need to use it. So to know that the space bar corresponds to a certain output and so on. But if you want, and if I had more time, I would go through the test. And so see, for example, look at the switch case and see where the solver is called, how it is called, where the correspondences are computed, and so on. But it should be quite straightforward. One thing more is that if you want, you can play around with this and change the camera model. Consider, for example, a radial camera or a different camera, and modify the files, the H and CPP files, correspondingly. In particular, assume that you want to change your camera and adopt a different model. Then the files that you should modify are the camera.h and the camera.cpp, of course. And these changes will reflect on the error and Jacobian, because of course the error and Jacobian calls the project point of the camera. And in case you're going to do this little exercise at home, then you should also recompute the Jacobian. Be aware of what you're doing in the Jacobian part. Okay, but in any way, this was an exercise to let you see a little bit of C++ applied to our probabilistic robotics domain. And it was for letting you see how to develop a complete application from scratch. Okay. Do you have any final questions? Okay, I suggest you to revise this, but of course, if you don't have much practice with C++, it's perfectly normal that you do not understand everything, but the idea should be clear. In any case, write an email if you need some specific suggestions. Okay, so I will stop the streaming. Check if there is someone in the chat and then stop the streaming.